about some different types of formulas. We talked about empirical and molecular formulas and how to calculate them. So again, for their empirical formula, we basically want to get whatever they give us into grams. We then want to convert grams to moles. We then want to divide by the smallest number of moles for each element. And again, as we talked about a number of times, if you do that and you do hit pretty much all whole numbers, you then will have your empirical formula basically. And again, we try not to round too much, but if it's really, really close to a whole number, just above it or maybe just below it, that's okay to round. Remember, if you don't hit a whole number, yeah, was that zero? No, I would say in general in textbook type problems, lab's a little bit different because it's more experimental, so sometimes we do a little bit more rounding. But in normal sort of textbook type problems, I would say anything that if you end up with, like a 0.33, even maybe a 0.25, point 0.5, any of those things. I would say if it is less than zero point 0.1, kind of above or below is probably okay. It kind of goes to the second decimal place, either above or below the whole number is probably okay to round. If you start getting into sort of kind of that first decimal place or so with some numbers, after you divide it, then it's probably too far to round, and you do need to find that common number. So I would say in most cases, 0.33 is a very common one, and zero point 0.5 also a very common sort of ending after you divide that you don't get a whole number. And again, these are definitely too far to round. So in these cases, again, you want to find a number to multiply the empirical formula by that will kind of turn these guys sort of into whole numbers and are very close to whole numbers. So for example, 0.33, if you multiplied it by 3, it's going to give you like a 0.99 type number, which is close enough to round to whatever that whole number would sort of be. Obviously, if you had like a 0.5, you multiply it by 2, that's going to get you to a whole number and stuff like that. So again, those are really too far to round, and those are probably, I would say, very common sort of too far to round endings that you would oftentimes get. Once you do get the empirical formula, when we talk about the molecular formula, there's really three things that you need. You do need the empirical formula. So either it will be given to you, or if it's not given to you, you obviously need to calculate the empirical formula. You do need the molar mass of the empirical formula. So either it's given to you or you calculate the empirical formula, then you could get the molar mass of it. And the last thing is you need the approximate molar mass of the compound. And this really oftentimes is given to you in kind of two different ways. A lot of times it will just be a sort of number, like it is approximately this much molar mass. As I mentioned before, you could also get sort of a range of numbers, like it's between like 80 and like 90 grams per mole, something like that. So regardless of which one it is, in most textbook problems, this is usually given to you. So somewhere in that problem, let's say something like that, like, hey, the approximate molar mass of this compound is this, or, somewhere between these two numbers and stuff like that. If it is the number, obviously you would use the number, as I mentioned earlier. If it's kind of a range, you could either use the lower end, you could use the higher end, or you could kind of go right in the middle. A lot of people kind of go in the middle of the two numbers and kind of use that as the molar mass. They will all give you pretty much the same sort of answer. What we do with that is we take the molar mass of the compound, which was given to you, and we divide it by the molar mass of the empirical formula, and this will give you a number. And this number, again, is the number that you multiply the empirical formula by to turn it into the molecular formula. As I also mentioned, here we are a little bit more, it's okay to do a little bit more rounding because a lot of times, for example, in problems, the apparent molar mass, it's just an approximation, so it's not perfectly what it is. So there is a little bit more room to sort of round and stuff like that. So again, the number there, will most likely be a whole number integer of our empirical formula. Any questions on that there? All right, so why don't you give this one a go? A phosphorus oxide contains 43.64 phosphorus and 56.36 oxygen. It's experimentally determined the molar mass is 283.89. What is the empirical molecular formula? Phosphorus is 3097. Oxygen is 16. Okay, so let's take a look and see here. So once again, we have percentages of each of the elements that are here. As we talked about last time, it's always a good idea just to kind of quickly add those together and make sure that you are near 100% or pretty close to 100%. Again, it may not be perfect, a little bit higher or low, depending on rounding. But obviously here, if we look at it, I got about 56 and 44%. So we're about 100%. We're not missing any type of element. In this case, we could assume, as we talked about, 100 grams. And really, the purpose of assuming 100 grams is it just keeps the numbers the same. So whatever the percentages are will be the grams. So that will basically turn our 43.54% of phosphorus into grams of phosphorus. We then could use the molar mass from the periodic table to convert those to moles, which is what we need to do. We could also do the same thing for our oxygen, which will turn it into 5636 grams of oxygen. Again, dividing by our 16 grams per mole, which is the molar mass of oxygen. That's going to give us the moles of each of these elements. So 4354 divided by 3097. We got a 1.4059 moles of phosphorus. We'll do 5636 divided by 16. We got a 3.5225 moles of oxygen. Any questions up to that point? So obviously here we are not given the empirical formula, which is necessary to calculate perhaps the molecular formula. So we're going to obviously be calculating our empirical formula here first. We want to divide by the smallest number of moles, which looks like in this particular case, it is the phosphorus that we want to divide everybody by. And if we do that for the phosphorus, that gives us a 1. And if we do that for the oxygen, we do not get a 1. We get a 2.5 in this case. So this would give us an empirical formula of PO 2.5. As we talked about before, these do need to be whole numbers. And also, as we talked about, that is definitely too far to round. So we do want to find, again, a common number to fix that with. And as we talked about, you pretty much could just figure it out there by trial and error. So obviously here we will end up with a 5 if we multiply by 2. Remember that we're actually multiplying by 2 to both of them. We're not making them 5s. Each of them are multiplying by 5, which is a common mistake. That will give us P2O5, and that should be our empirical formula in this particular case. Any questions on that one there? All right, so we multiply by 2. The 3 things that we need for the molecular formula is we need the empirical formula, which we just calculated. We will need the molar mass of the empirical formula, and we will need the molar mass of the compound, which was given to us before I put a line through it. And I'm going to get rid of that there. There it is. It's 283.89. So that is what was given to us here. So we'll calculate our molar mass of our empirical formula. So that's going to give us 2 times 3097 for the 2 phosphorus. We're going to add it to 5 times 16 for the 5 oxygens that are present. And that's going to give us a molar mass of our empirical formula of 2 times 3097 plus 5 times 16. That'll give us a 141.94 grams per mole. Now that we have our empirical formula and the molar mass, and obviously we have the molar mass of the compound given to us, that again is all we need. We're going to take the molar mass of the compound, 283.89. We're going to divide it by the molar mass of our empirical formula. And again, that's going to get us a number here, 283.89 divided by 141.94. Gets us about a 2. That again is the factor that we're going to multiply our empirical formula by, and that will give us a P4O10 as our molecular formula. Any questions on those calculations there? Now, this is a pretty good approach to doing these type of problems. We also have an option to do these problems a little bit different because in this case, we do have the percentage of each of the elements, and we do know the molar mass of the actual compound is. If we wanted to, we could essentially kind of work backwards, and you could actually get the molecular formula first and then kind of get the empirical formula from that. Just to show you how that calculation will work, let me just take our numbers here. So if we were to take the same problem where we had, it was 4364 phosphorus and 36% oxygen, and our molar mass of our compound was 283.89 grams per mole, basically, or grams. So what we know is this is the percentage by mass of each of these elements. So if we convert these percentages by mass into decimals, divide by 100, that gives us 0.4364, which is basically 43% of 283.89 grams, which is the molar mass of this compound, would be made up of phosphorus in this case. So if we take 0.4364 times 283.89, we get something like 123.8896 grams of phosphorus. If we divide that by the molar mass of phosphorus, which is 3097 grams per mole, we will end up with 4 moles of phosphorus. We could do the same thing for our oxygen to convert this into a decimal, divide by 100, 0.5636 of that 283.89 grams is basically made up of oxygen. So if we do that, 0.5636 times 283.89 gives us 160.00, basically grams of oxygen, divided by the molar mass of oxygen, which from the periodic table, which is 16 grams per mole. And that would get us basically 10 moles of oxygen. That would give us not our empirical formula, but it would give us our molecular formula right here. And then at that point, we could divide everybody by 2, and that would get us to P2O5, reduce it down by 2. And that will give us our simplest whole number ratio, which would give us our empirical formula. So if you do have the percent composition by mass and you do know the molar mass of the compound, you basically can multiply the molar mass of the compound by the percentage of each element, convert it to a decimal, and then divide by the molar mass of those elements, and that'll give you the moles of each of those guys, and that will get you your molecular formula first, and then you can just reduce it down to the simplest whole number at that point to get to your empirical formula. As you can see, they both give you the same answers, so whichever way you like, you could go. This is a good way, again, if you have the percentages given to you. If you don't, then you might as well just go the other way. No sense figuring out the percentages and have to kind of go backwards and all that kind of stuff. Any questions on that there? All right, so let's try one more here. Vitamin C contains carbon, hydrogen, and oxygen, and has a molar mass of 176.13. What is the empirical and molecular formula? Carbon 12.01, hydrogen 1.008, and our oxygen here going to be 16. Okay, let's take a look. Once again here, we're looking for both the empirical and molecular formula. And obviously for the molecular formula, we do need the empirical formula, which we don't have, so we do need to calculate it. We do need the molar mass there of our empirical formula, and we do need the molar mass there of the compound, which is given to us. So if we take kind of our normal approach to this, we want to look at our percentages here, and they do add up to about 100. So we're just going to assume 100 grams. And that will give us 40.9 grams of carbon, which we then want to divide by the molar mass of carbon, 12.01. That will give us 4.58 grams of hydrogen, which we want to divide by the molar mass there of hydrogen. And that will give us 54.5 grams of oxygen, which we want to divide by the molar mass there of oxygen in this case. That's going to get us here 40.9 divided by 12.01. Will give us a 3.405 moles of carbon. We'll go 4.58 divided by 1.008. Going to go 4.5437 moles of hydrogen, and 54.5 divided by 16, 3.406 moles of oxygen. Here we're going to divide by the smallest, which is fairly close on two of them, but it does look like perhaps carbon is just a little bit smaller, maybe. So we'll divide by that, 3.405 moles. It's going to give us a 1 there. That'll give us a 1 there, and a 1.33, I believe, there. That gives us an empirical formula of CH 1.33 and O. Again, 1.33 is not a whole number and too far to round. So again, if you do like 1.33 times 1, that's 1.33. 1.33 times 2, 2.66. 1.33 times 3 is 3.99, and that's pretty close to 4. So we will go by this factor of 3 to multiply by. And that will give us then, if we multiply this by the factor of 3, C3H4O3, I believe, in this case. And that would be our empirical formula. Any questions up to there? Now that we do have our empirical formula, we're going to get the molar mass of it. So we will take 3 times our 12.01 for our carbons, plus 4 times 1.008 for our hydrogens, plus 3 times 16 there for our oxygens, and that will get us 3 times 12.01 plus 4 times 1.008 plus 3 times a 16 to get us at 86.06 grams per mole as the molar mass of our empirical formula. We obviously have our compound's molar mass, so now we can take 176.13 divided by 8606 here. And if we do that, 176.13 divided by 86.06, going to give us about a 2.04. And again, that is pretty close to a 2. So we will multiply our empirical formula by that factor of 2, and that will give us C6H8O6 as our molecular formula. Any questions on that one there? Now, again, this is one where you could, again, use the percentages and kind of go molecular formula first. So if we did that, and just to show you how to do it the other way one more time here before we wrap it up. Here, this. So if you take sort of the other approach, kind of going for the molecular formula first, and again, we could do this because we do have the percentages and the molar mass, and it's sort of a single number there. We will turn our carbon into a decimal by dividing by 100, so 0.409 times the molar mass of the compound. and that's going to get us 0.409 times 176.13. That'll give that 176 grams. It's about 7204 grams of carbon. We'll then divide by the molar mass of carbon, which is 12.01 grams per mole. And that'll give us about 5.998, which is pretty close to 6 moles of carbon. We'll do the same thing. We'll take our hydrogen divided by 100, or move the decimal place 2 places to the left, and we'll multiply it by the molar mass for hydrogen, 0.0458 times 176.13. That's going to give us about 8.0668 grams of hydrogen divided by the molar mass of hydrogen. Going to give us about 8 moles of hydrogen. And lastly, 0.545 times our 176.13 grams for our oxygen. Going to get us about 95.9909 grams of oxygen divided by molar mass of oxygen, 16 grams per mole. Going to get us again about 5.999, which is pretty close to 6 moles of oxygen. That again, if you take this approach, will give you not your empirical formula, but will hit you with the molecular formula like we got down here first. At that point, you can look and see you basically could reduce everybody down by 2. So we're going to divide everybody by 2 and still have whole numbers, and that will take us to C3H4O3 as our empirical formula. So again, either approach obviously gets you in the same spot. And that works because it is based off of percent composition by mass, and so it works out the same way. Any questions on how to calculate empirical formulas, molecular formulas, any of those things? So, all right, so I think that should wrap this chapter. It does. And I believe that should be the final bit that will be on our exam coming up on Monday. So that's up through here. Any questions on that there? All right, we're going to then go on to the next bit of topics here. So we're going to kind of pick and choose as a couple of different chapters for this stuff. So in this chapter, we're going to talk about balancing equations and equations in general. We're also going to talk about reactions and types of reactions and ways to classify reactions. And we'll even get into a little bit of some stuff that's maybe like chapter 17, some redox type information that will be here. So we're going to start with just the basics of a chemical reaction and a chemical equation. Obviously, a chemical reaction involves a chemical change, and a chemical change is pretty much happens when whatever you start with fundamentally changes to something else, and you can't get back the original substances by any types of physical means. You can't boil it, freeze it, melt it, whatever it may be, separate it out. Now, when we do have a chemical reaction, as we talked about, say with bonding and those type of things, really the only thing that happens in a chemical reaction is all of the reactants or the starting material break their bonds, and then they basically reform on the other side. Because as we talked about, the most important thing in terms of an element and what element we're talking about when we talk about protons, electrons, and neutrons, which one determines the element? It is the protons, right? The atomic number. So in a chemical reaction, because it only involves electrons, it doesn't involve anything in the nucleus, we do have conservation of elements as we go from starting to ending. They just end up in different sort of formulas and compounds on the product side. We do not change any elements, which means basically when we use an equation or have an equation, it should always be balanced, which means if we started with 6 carbons on the left-hand side of the arrow, we should end up with 6 carbons on the right-hand side of the arrow. They may be, again, in different things. So when we look at a reaction, on the left-hand side of the arrow are our reactants, and these are our starting material. in a chemical reaction. And on the right-hand side of the arrow are our products, and that is what is formed as a result of a chemical reaction. So pretty much in this case, these guys are going to break their bonds. This guy will break their bonds, and they will reassemble on the other side with new bonds. But as you can see here, we started with 2 oxygens, still have 2 oxygens. We started with a grand total of 4 hydrogens, still have 4 hydrogens grand total. Again, we don't lose any elements along the way. So when we look at a chemical reaction, it's always reactants to products. Other things that we sometimes will see in a chemical reaction are the states of matter. So S is solid if it is next to it. L is liquid if it is next to a formula. G is gas. And AQ is aqueous. And that's basically a water environment. So there is a difference between L, which is a liquid, and AQ, which is aqueous. They both are in the sort of physical state of a liquid, but the difference is when you have something, for example, that is a liquid, like water, you have basically one thing by itself. So water is a pure liquid. Now, if you take something like water, and as we'll talk about, you take something like sodium chloride, which is a salt, those sodium chloride will basically dissolve in the water, and you will end up with a sodium chloride solution, which would be aqueous, and that is what has an aqueous thing. So aqueous is basically a solution. It is a homogeneous mixture. Basically, you take 2 things or more than 2 things, or at least 2 things, and dissolve it in each other and so forth. A liquid is something that is just pure sort of substance by itself. So again, there are differences in that. In equations, we oftentimes will see that. In addition, when we look at the arrow, we will also sometimes see things written on top of the arrow. For example, if you have a little triangle or delta symbol, that oftentimes means heat is being applied. A lot of times as well, if you kind of look over the arrow, a catalyst will be placed there. So catalyst can be something like, say, PT, like a metal. It could be something like H plus, which means an acid. And that's basically something that is used to speed up the chemical reaction. Yeah. No, AQ is AQ actually means aqueous, and it is used for acids. And because an acid is basically an aqueous solution, that allows that H plus to basically be released in the solution. So it's oftentimes used to distinguish something as being an acid. So for example, if you had like HCl, it could be a gas, or you could have HCl with the aqueous here, which is a acid, which is hydrochloric acid. So aqueous is oftentimes used for acids because basically the definition of an acid is the ability of an acid to basically release its H plus in solution in a solution sort of environment. This would be hydrogen chloride gas, and that would obviously be in the gas form. You get this by like bubbling that through water, and you will produce basically this guy actually. But aqueous, AQ does mean aqueous. It means basically a water environment. It usually means something that's been dissolved in water. Like in this case, HCl gas kind of bubble through water, gets dissolved in water, and now they become sort of ions that are floating around in the solution. Other questions? So a catalyst, by the way, is a catalyst is not a reactant. It is not a product, and it actually does not get used up in the reaction. So a catalyst is really there to, in most cases, facilitate that reaction happening a lot faster. So it usually will speed up a reaction. There are actually catalysts that will slow down a reaction, and they're sometimes referred to as negative catalysts. But I would say probably 99 times out of 100, somebody's talking about a catalyst, they're talking about it in the sense of speeding up the reaction and making it occur quicker. And we'll get into it maybe a little later on. But basically, there are different ways a catalyst works. For example, a catalyst can be a metal, which is a very common thing. And what it does is, for example, instead of like gas molecules flying around trying to find each other for the reaction to take place, it provides like a central location that like the gas molecules are attracted to, and that's then going to allow them to sort of mix and start reacting with each other a lot quicker. Also, something like an acid being used as a catalyst will provide the right environment, sometimes maybe the right pH for a reaction to basically take place. So catalysts typically there to speed up a reaction, not considered a reactant, not considered a product, still there at the end of the reaction and does not get used up in the reaction. So when we look at an equation, there are different ways to read it. When we look at the coefficients in the equation, and much like everything else in chemistry, if there is not a coefficient written, it is assumed to be 1. And again, we typically don't write 1, but again, it's assumed to be 1. We can say that the 2 atoms of magnesium react with 1 molecule of O2 to give us 2 formula units of magnesium oxide. Formula units is sometimes used for ionic compounds. Um, and just like molar mass, sometimes formula mass is used for that. And this is a word is sometimes used for ionic compounds because technically they're not sharing electrons. So sometimes people don't use molar mass for them or molecular mass because they're not molecules. In that sense, they're basically held together by those electrostatic attractions. So sometimes formula units are used in describing ionic compounds. We could say this relationship here, which we will see a lot and you might be familiar with as well. This is sometimes referred to as the mole to mole relationship that you could get from a balanced equation. And that could say that 2 moles of magnesium react with 1 mole of oxygen gives you 2 moles of magnesium oxide. This is our conservation of mass because we basically have 2 magnesiums and 2 oxygens. That's 48 grams of magnesium and 32 grams of oxygen will make 80.6 grams of magnesium oxide. We also have 80.6 grams of it on the other side. We do not use a gram to gram relationship. That's the only relationship that we don't use. Later on, when we talk about stoichiometry, that's going to be the major sort of relationship that we can get from the equation, and we can use the equation as a conversion factor to do calculations that we need to. So when we balance the equation, there's a couple of sort of steps to use, but most people will do some type of uh, sort of trial and error, I guess is the best way that people kind of do it. There are certain things that you can look at when you balance the equation that could help you, but a couple of really important things when we do balance the equation and when we do have the equation completely balanced, uh, all of the coefficients, and that is, by the way, the only thing that we can change when we are balancing an equation, all the coefficients need to be whole numbers. They also need to be the simplest set of whole numbers. And what I mean by that is, let's just say you balance this equation, 2a plus 4b gives you 6c, and this is a balanced equation. Again, we only change the coefficients. We never change the subscripts. If we change the subscripts in the formula, we just change what it is. So we never touch those things. So we never put anything other than the number that comes in front is the only thing that we change. Never the subscripts, never put numbers like in the middle or anything weird like that. So always just the guy in front gets changed, nothing else. So if we did balance equation, this was balanced per se, and we did have the same number of elements on each side, we could see that by looking at the coefficients, we could actually reduce down all the coefficients by 2 and end up with a plus 2b goes to 3c, and we would still have all whole numbers, and this would be the properly balanced equation. So this does sometimes happen because sometimes people can see larger numbers to balance the equations and stuff like that. So if you're able to, at the end of balancing the equation, go through all the coefficients and reduce them down by a common number and still have a whole number, then you should do that to have the properly balanced equation when you do that. So personally, for me, when I balance equations, I just try to keep it simple. What seems like the easiest thing to sort of balance is probably the best thing to start with. A lot of times that is things that are only in one sort of location on each side of the equation. Things that are in multiple formulas, elements and multiple formulas, you might want to leave towards the end and kind of pick it up that way. So the first thing that you want to do is if you happen to be given anything in words, so maybe you're just given all words of how this equation is going to react, you definitely want to make sure that you do start out with the correct formulas. This is also very common if you're given reactants and you have to predict what's on the product side and then balance the equation. It's always really important that to make sure that you start out with the proper formulas first and then do the balancing. That is the proper order. Formulas first, then balancing. Very common, and especially in this case, you see it a lot where people have the front end of the equation and then has to predict what's on the right-hand side and also balance it, is they try to write formulas and balance the equation at the same time. And what ends up happening is you end up with wrong formulas. You'll never get the thing to balance because you don't have the right formulas. So it's really important just to start out with the right formulas, regardless of the balancing. So in this case, ethane reacts with oxygen. So that is ethane, that is oxygen. Also remembering that if you have anything like oxygen, molecular oxygen, oxygen gas, or hydrogen, nitrogen, those type of guys, those are diatomic molecules, right? So they're like O2, H2, and they're by themselves. So you got to make sure that you, again, are starting with the right formulas. So if you have something like hydrogen gas or molecular hydrogen, you write just H and go to balance your equation, you're going to get it wrong because you're not starting again with the right formulas. Carbon dioxide to form basically means the arrow, and carbon dioxide is CO2 and water is H2O. So at this point, I have my equation written here. It is considered to be unbalanced at this point, but I don't care because I just have the equation, and that is what I am looking for to start with. I have all the right formulas in my unbalanced equation. I personally, when I go to balance equation, make a little table. It just helps direct you maybe where you might want to start. So for example, I have a reactant side, I have a product side, and I have carbon, hydrogen, and oxygen in this case. And on the reactant side, I have 2 carbons, which is here. On the product side, I have 1 carbon, which is there. Reactant side, I got 6 hydrogens. Product side, I got 2 hydrogens. And oxygen here on the left is 2. And on the right, we need to make sure we get everybody. So I do have 2 on the left on the right-hand side there in the CO2 and 1 in the water, which is a total of 3. So making a little table is, again, sometimes really helpful because it does oftentimes sort of help you sort of figure out maybe where you want to start. So in this particular case, for me, just looking at the table, carbon seems like a pretty good place to start with. You could very easily fix carbon by just simply putting a coefficient on the right-hand side of 2. And when I do that on the right-hand side, I now have 2 carbons. In terms of hydrogen, I still have 2. And when you do put a coefficient, it does go for everybody that's behind it. So in this case, that would give me 4 oxygens and 1 more here would give me 5 oxygens at this point. Now, when I look at my table, I could clearly see that hydrogen is probably going to be the next easiest thing to balance. The reason I am not perhaps going after oxygen at this point is when I look at oxygen, I have oxygen by itself over here, but then I have oxygen in a couple of things over here on the right-hand side. So there's a lot of things sort of tied to oxygen on the right. So that's probably going to mess some other things up. So best to maybe save that for the end, and things will hopefully fall into place. So because of that, I am going to go after the hydrogen, which is obviously pretty simple to fix. On the left-hand side, we have 6. On the right-hand side, we have 2. So once again, coefficient, I will put a 3 in front of my water. Once again, that is going to go for everybody behind it. That will give me 2 carbons. 3 times 2 is 6 hydrogens. And now in terms of oxygen, I have 4 up here in the first guy. And I also have 3 times 1, which is 3 in the second guy. And that is going to give me a 7 here. Any questions on that so far? So if I look at what I got going on at this point, I got here C2H6 plus O2 gives me 2CO2 plus 3H2O. If I look at my table, carbon is good, hydrogen is good. Now what I have left is oxygen. I got 7 on the right-hand side. I have 2 on the left-hand side in this case. I clearly probably don't want to play with any of the coefficients on the right-hand side since those are all kind of balanced with the carbons and the hydrogen. That means really my only option at this point is to play with the O2 on the left-hand side. And that means I needed to basically turn that 2 into a 7. And in this case, you could do that by a fraction. So you could go with 7/2 if you like. And if I do that, I will end up with 2 carbons, 6 hydrogens, and when I take 7/2 times 2, the 2's cancel, gives me 7 in terms of my oxygen. At this point, this equation is balanced. Can I keep it like that, though? I cannot, because remember that all of the coefficients need to be whole numbers, and clearly that is a fraction. So this demonstrates a good point that sometimes you do need to use a fraction to balance the equation, but you cannot leave the fraction, so you do have to clear the fraction. So to clear the fraction here, we would multiply everything in the equation by the coefficient, or no, I'm sorry, by the denominator there, which is 2. And that would give me 2C2H6 plus 7O2 goes to 4CO2 plus 6H2O. And if I didn't screw everything up, we should still be balanced here. We have 2 times 2, which is 4 carbons on the left, 4 on the right. We have 2 times 6 here, which is 12 hydrogens on the left, and 6 times 2, which is 12 on the right. Oxygen, 7 times 2 is 14. Oxygen on the left, I have 8 oxygens there and 6 on the second guy, and that also should be 14. So I am balanced in this particular case as well. First off, any questions on that there? How do you choose the fraction? The fraction is pretty simple to choose. Basically, when you go to choose the fraction, for example, like this, the number on top is the number you need. So if you remember, I needed a 7 there up on top, and the number on the bottom should match that number, and you always have the right fraction. So basically, number on top, the one you need, number on the bottom should match the subscript to that, and you'll be in good shape. I would say this happens a lot, especially when you have an elemental diatomic molecule by itself on one side and that element and a couple of things on the other side. So that very commonly sort of happens when you have to use a fraction. Any questions on that there? Yeah. All right. That's what we just did. Roll that through in case you want to look at it. All right, so why don't you try one here, balance this equation, see what you come up with. Okay, so let's take a look at it here. So it's gonna make a little table, reactant side, product side. Gonna list my elements. I got nitrogen, oxygen, hydrogen. On the left-hand side, I have 1 nitrogen there. I got 2 nitrogens there on the right, 1 oxygen on the left, 1 on the right, and 2 hydrogens on the left, and 2 hydrogen on the right. So again, from my table here, I can see pretty much everything's balanced except for nitrogen. So it seems like a good place to start. So we can simply fix that by putting a 2 in front of the nitrogen. That's going to again go for everybody behind it. That's going to give me 2 nitrogens. We will then have 2 oxygens and still 2 hydrogens. And this is very common as you balance the equation. You'll kind of fix one thing, kind of screw up something else. So now we can clearly see it is the oxygen in this case that is not balanced. So we could fix the one on the right by again putting a 2 in front of the oxygen. That's going to give us 2 nitrogens. Once again, this 2 will go for everybody behind it. So that is going to be 2 oxygens, and 2 times 2 is 4 hydrogens. So now we fixed everything but messed up the hydrogens, which can be easily fixed by just putting a 2 there on the left-hand side, giving us A2, and A4. And now we are balanced with all whole numbers. Any questions on that one there? All right, we will lay it up there